back. This is the second lecture of our course. Let me remind you that in the previous lecture, we proved exponential lower bounds from the weak ETH assumption, from the exponential time hypothesis. In this lecture, we'll be using SETH, the strong version of this hypothesis, and we'll see that under this hypothesis, we can prove not only exponential lower bounds, but even polynomial lower bounds for some problems in P. And in the following lectures, we'll see that actually we can use these assumptions for many different kind of bounds. Like we'll prove super exponential lower bounds, we'll prove polynomial lower bounds for problems in P. Okay, so we start with problems which are solvable in polynomial time, and we'll prove that it's hard to improve on their running time, that any improvement will basically lead to a breakthrough algorithm for the satisfiability problem. Okay, we'll start with the orthogonal vectors problem. Let me first define it. You have two sets. Each of them has n d-dimensional 0, 1 vectors. And the question is to find two orthogonal vectors. That is to find one vector in the first set, another vector in the second set, such that their inner product is 0. How can we solve this problem? Like the trivial algorithm would be to try each pair, one vector from the first set, one vector from the second set, and compute their inner product. Computing inner product in d dimensions costs only O of d time. So the total running time will be n squared times d. Now we'll show that actually under the strong ETH assumption, one cannot significantly improve it. Basically, for almost for any superlogarithmic d, an algorithm which runs in time n to the 2 minus epsilon for any constant epsilon would be a breakthrough algorithm for SAT. Are there any questions? Is the problem clear? We're going to be proving.
The summation is over F2 field?
No, the summation is over say reals. Yeah, I meant 0, 1 vectors in say R to the d. Yeah, the inner product is over the reals. Vectors are going to be 0, 1 vectors only.
Just to join those?
Yeah, this is basically just flipped. Yeah.
They don't have common 1?
Right, they don't share a 1. For example, so what the problem looks like, this is S, namely this is n, say rows. Each of them is of length d, it will say 0, 1, 0, 1, 0, 1. This is T, which looks the same, just contains maybe different rows. And you want to find a string here and a string here, such that they never share a 1. If there is a 1 at this position, then this must have a 0. Okay, so the algorithm is still trivial. Let's try to prove the lower bound. Let's try to say that if one can solve the orthogonal vectors problem in time n to the 2 minus epsilon, then we solve SAT. Okay, so we're going to reduce SAT to orthogonal vectors. Assume you give me a KCNF phi, I'm going to split its n variables into two groups of size n over 2. Now this is yet informal. For each assignment to the first n over 2 variables, I'll create a vector in S. For each assignment to the second n over 2 variables, I'm going to create a vector in C. That's what my reduction will look like. I will explain how I create those vectors. So I will have an instance of orthogonal vectors with that many vectors, 2 to the n over 2, because this is the number of assignments to n over 2 variables. And the dimension d will be m, number of clauses. So here, if my original formula has n variables, m clauses, I will have 2 to the n over 2 rows in each table and m number of clauses columns. And by specification lemma, we know that m can, like, we can reduce m to linear, and so it's like, it's just logarithmic in n anyway. Okay, how does the reduction work? So look at the assignment to the first n over 2 variables. This is a binary string of length n over 2. Now we look at all clauses of the given ksat formula, and if this assignment, this is not full assignment to all variables, only like to the first n over 2, but even if assignment to the first n over 2 variables already satisfies some clause, then we write 0 in the ith position of the corresponding vector. If it doesn't satisfy, then we write 1. Again, for each assignment, for each clause, we write either 0 or 1. How do we understand whether it's 0 or 1? We look if this partial assignments to n over 2 variables only satisfies this clause number I. If it doesn't, we write 1. If it does, we write 0. Is it good? We do the same for the second half of the variables, and we just, this way we compose the table C. Now I want to say that this formula phi is satisfiable if and only if there exists an assignment to the first n over 2 variables, an assignment to the second n over 2 variables, such that for every clause, which actually corresponds to a column in my tables, such that for every clause, either this one is 0 or this one is 0. Every clause must be satisfied by a variable in the first or second half. So I must have a 0 either here or here. And this is exactly the orthogonal vector problem. I want to find a vector in the first half, a vector in the second half, such that their inner product is 0. Cool. So now assume I have a subquadratic algorithm for orthogonal vectors. I assume I can solve it in time to n to the 2 minus epsilon for constant epsilon. Then I reduce SAT as I just showed, and then I have running time for ksat n to the 2 minus epsilon, where n, this n from the orthogonal vectors problem, is 2 to the n over 2 in terms of the number of variables of the original SAT formula. So I spend time roughly 2 to the n over 2 to construct those tables, and then I solve the orthogonal vectors problem in this squared minus epsilon. And this gives me total running time 2 to the n minus linear function of n for every single epsilon. So for fixed epsilon, you improve. If you improve quadratic time algorithm for orthogonal vectors, you automatically get a good algorithm for SAT. It's clear? This result was first proved by Ryan Williams in 2005. If you can solve it for any super logarithmic, then this would work for me, because once I reduce SAT, yeah. I just ask, I don't know for what constant times log n I want you to solve it. I just say, solve it for every super constant times log n, and then I'm good. Okay. Let's see one more example of problem from P, for which we can give a tight lower bound from the strong exponential time hypothesis. So the dominating set problem. K dominating set is defined the following way. You are given an undirected graph on n vertices, and you want to find a set of vertices of size at most k, such that you dominate all vertices of the graph. What does it mean to dominate? If you take a vertex, you dominate it. If you are neighboring a vertex, you still dominate it. So you want to cover all vertices of the graph by taking either those vertices or their neighbors. for every vertex of the graph, you either take it in your set or you take a neighbor of it.
You can't.
Sorry?
You can't.
I can't hear you.
You can't.
It's not the click problem, no, it's a different one. They both are NP hard, but this is a different problem. For example, if you have such a graph, like a star graph, the largest click you have here is of size 1. Oh, yeah, what example problem. Say you have such a graph. Yeah, here you have a triangle, a click of size 3, but you can dominate all vertices just by taking this one. Okay, yeah, so this is a k-dominating set problem. How fast can we solve it? A natural approach would be to consider all sets of size k, and for each of them check whether it is a dominating set or not. Once I have a fixed set of k vertices, I can probably check whether it is a dominating set or not in like roughly linear time. For each vertex, I will check whether it is neighboring one of my vertices. Okay, so I can go through all sets of size k in time n to the k. And then in additional time n, I can verify whether it's a dominating set or not. So I can solve it in time n to the k plus 1. Actually, for large enough k, I can solve it in time n to the k. That was shown by Petrashko and Williams in 2010. We'll see it in a second. When k is at least 7, I can solve it in time roughly n to the k. And under the strong exponential time hypothesis, there is no way to improve it. You cannot improve it by any constant here in the exponent. We'll prove it in a couple of seconds too, yeah. So for dominating set problem, basically for any k greater than 7, we can solve it in time n to the k, but any improvement, just constant improvement here in the exponent would lead to a breakthrough in SAT. Okay, first let's see this algorithm. Let's see this upper bound. You give me an undirected graph G, I will write its adjacency matrix A, and I will also write once in the main diagonal. This would basically be like self-loops of the graph. And let's first see the two-dominating set problem, like k-dominating set problem for this, like very special case when k is 2. Assume two vertices u and v form a two-dominating set. Then what does it mean? This means that for every I either is u or v or one of its neighbors. Since I already have ones on the diagonal, like I have self loops, then I can just say for every vertex I have either ai, u or ai, v. Does it make sense? Every vertex is covered either by u or by v. Okay, in other words, I can say that for every I, this product is 0. 1 minus aiu times 1 minus avi. I flipped, I flipped the order of variables here, but this undirected graph, it doesn't matter. But this way it's easier to see that this is actually just matrix product. If instead of A, I consider its complement 1 minus A, then I'm just saying that product of A with its transpose contains a 0. So again, I have a pair of vertices which have a two-dominating set if and only if the product of these two matrices contains a 0. How can I check it? I can easily construct this matrix in n squared time. This is the size of the matrix. I can actually multiply two n by n matrices in time much faster than n cubed, with a recent record of n to the 2.373 by Vasilevsky, Williams, and Le Gaulle. So I construct these matrices in time n squared, then I multiply them in time n to the 2.4, and that's it. I just check if my matrix of size n squared contains a 0, which I clearly can do in quadratic time as well. So this is a way to solve two-dominating set problem in time n to the 2.4, which is much better than n to the k plus 1, which would be n cubed. And actually, this approach works for all k's, for all values of k, but starting from k equals 7, it gives us even better running time. So how do we do this for k-dominating set? I list all k over 2 tuples of vertices. And for each set of k over 2 vertices, I look at all vertices dominated by them. I construct the same matrix A, just this time it's rectangular. For each k over 2 tuple, I list all out of n vertices which are dominated. I have two matrices like this, like k over 2 tuples, k over 2 tuples. Now to check that there is a dominating set of size k, I again need to check that this k over 2 covers all, like some vertices, and the remaining k over 2 chosen vertices cover all the remaining vertices. So again, I just need to look at the product of two matrices, just this time they are rectangular. Is it clear? Instead of, like in the previous example, we were looking just at sets of one vertex each. Now we're looking at k over 2 tuples. Okay, very good. And there is a famous result by Coppersmith from 1997, which says that a product of rectangular matrices can be done in optimal time. I mean, in the time which is basically the size of the output. As long as the dimensions of the matrices differ like significantly. I can multiply matrix of size n times n to the like basically 0.3 in time n squared, which is proportional to the output size. And when k is at least 7, here I have basically a matrix of size n to the 3.5 times n, and yeah, so I can actually use this result by Coppersmith. And I can multiply them in time which is square of their largest dimension. Largest dimension is n to the k over 2. Its square is n to the k. So again, I can solve this k-dominating set problem in basically square of this matrix size, which is n to the k over 2. This gives me n to the k algorithm and improves on the n to the k plus 1. Any questions? So we just showed that we can solve k-dominating set problem in time n to the k, and now we'll show that any improvement on this would actually imply a non-trivial algorithm for SAT. Okay, for this again, I start with the CNF formula on n variables, and I'm going to reduce it to the k-dominating set problem for every k. So I partition the input variables, n of them, into k groups evenly. Each group is of size n over k. I can assume without loss of generality that n is divisible by k. Okay, I'll be asking you to find a dominating set of size k in the following graph. First, for the first group of n over k variables, I draw here 2 to the n over k vertices. Each of them corresponds to a Boolean assignment to this n over k variables. There are 2 to the n over k ways to assign zeros and ones. So that's how many vertices I have here. And then I add just one dummy vertex. It is connected to all of them, and it's not going to be connected to anything else in the graph. It's just a dummy vertex for this specific gadget. I do this for the remaining k-1 groups as well. So I have k parts. Each of them is a clique of the size 2 to the n over k plus 1. Okay, now I need to take care of the clauses of the original formula as well. Now I introduce like basically gadgets for them. I have m clauses. For each of them I add one vertex. And now I connect a vertex corresponding to an assignment to a vertex corresponding to a clause if and only if this partial assignment satisfies this clause. If clause is satisfied, it is connected to the vertices that satisfy it. That's it. Now I want to say that this graph contains a dominating set of size k if and only if the original formula was satisfiable. The first direction, so we prove it as always, like we prove two directions. Assume the formula is satisfiable. Then this means there exists an assignment to all n variables. I can split it into k assignments to each of the groups, and I take the corresponding vertices here. So I'll have exactly one vertex in each group. Clearly it dominates all of this, and they together must dominate all the clauses because this is satisfying an assignment. In the other direction, assume I have a dominating set of size at most vertex. For this, I have to take one of the vertices here. Same here, I have to dominate this dummy vertex. I take at least one here, at least one here. So but my total budget is k. So from each group, I must take exactly one vertex. And since I dominate these clauses and a vertex is connected to a clause only if it satisfies it, I satisfy all m clauses. So yeah, we just reduced SAT to dominating set. And let's see how many vertices we have here. We started with a SAT on n variables, m clauses. We have k gadgets, each of them had 2 to the n over k plus 1 vertices. And we had additional m vertices for clauses. And by, say, specification lemma, we know that m is small comparing to this, k is constant, so this is basically 2 to the n over k. And if you can solve the k dominating set problem in time better than n to the k minus epsilon, then this gives me the running time for SAT 2 to the n over k times k minus epsilon, which again exponentially improves on the known algorithms. Any questions? Yeah.
This term vanishes as k grows to infinity. And this contradicts.
K is constant here. We're talking about k dominating set for constant k. Yeah.
So, but I don't understand the claim. If SATH fails, then, sorry.
No, if for any k, for example, you can solve 7 dominating set in time n to the 6.5. You broke SATH. Say you can solve 12 dominating set in time n to the 11.9. You just broke SATH.
This is k, it's not k set.
No, I'm reducing general SAT. K is a k dominating set problem.
Okay, so we started with general.
Well, we started with general SAT. I can, like in this specific case, I can reduce even general SAT. This is not always the case. We'll see in a minute that sometimes I have to use the full power of strong ETH assumption, saying that you can start from k SATs for arbitrary large k. Here I don't even need this. I say I reduce general SAT with arbitrary closed lengths. That's good? So yeah, if you improve on dominating set for any k, on k dominating set, then you already like break SATH. Yeah?
When we form a dominating set,
Sorry?
when we form a dominating set on the previous slide,
Right.
so it's the other direction from dominating set to satisfiability. So we have, you claim that we have to take all the vertices inside the clicks, so we do not take dummy vertices and we don't take the close vertices.
When we go from a Boolean assignment to dominating set, yeah, we don't take them. In the other direction,
Suppose we have a dominating set that contains at least one dummy vertex.
right. If it takes this vertex, then it means that actually it doesn't matter whatever assignment you take here. Even without this first group of variables, you already satisfy all the clauses. So on the first n over k variables, you can take whatever assignment you want.
Because it's satisfied by just another click.
Yeah, because all clauses happen to be satisfied by the other groups. More questions? Okay, now let's see the heat and set problem. That was the first non-trivial lower bound from SETH. We start with a very simple lower bound and eventually build up to a tight lower bound. So the heat and set problem. You have m sets over the universe of size n. Basically, you have a huge set of size n and then m subsets of it. You want to find a small set, like a small subset of 1 to the n, such that each of the given sets intersects it. So you have, again, this is your universe of size n, basically numbers from 1 to n. And you have sets f1 to fm, like this set, like, this set and something else. And that I meant like it's set which contains this and this, but doesn't contain anything in between. And you want to find a smaller set which hits all of them. For example, you can take this and this elements. This element hit this element hit this, and if you also had such a set, you still hit all three of them by taking only 2 elements. So you want to find a hitting set of minimum size in this problem. What is the trivial upper bound for this algorithm? You can go over all sets. There are all subsets. There are 2 to the n of them. And just check that you hit all of the input sets. You can do this in some polynomial time. So trivial upper bound is 2 to the n. Eventually we'll show that actually under the strong ETH assumption this bound is tight. Any questions about the problem? Okay, we'll start with a very simple lower bound, not tight yet. Again, I want to reduce SAT to the heating set problem. I start with the formula phi, again, just general CNF, not necessarily general CNF, not necessarily KCNF. And for each variable, there are n variables. For each of them, I create 2 elements in my universe. My elements here are not called 1 to n anymore. They're called T sub x, F sub x for every out of n variables x. And my family of sets will be, for every variable, I add the following set. Tx, fx. Tx will correspond to like x being true, and fx will correspond to x being false. I'll ask you to find heating set of size n. I'll just add a few sets to my collection first. For each clause, for example, for such a clause, x1, negation of x2, x3, x4, I add the corresponding clause to the family of sets. This is calligraphic F. So I'm just saying that either x1 must be true or x2, this x2 must be false, or x3 must be true or x4 must be true. You have to satisfy this clause. So I add such a set to my family. Now I'm saying that this construction has a heating set of size n if and only if there is a satisfying assignment to the original Boolean formula. And this is kind of trivial because since your budget is n and you have n sets like this, you have to take exactly 1 for each variable, either true or false.
Why can't you take both?
Because you have n sets like this, and your budget for the heating set is n. Yeah, they all are disjoint. You have to take n elements, yeah, you have to take 1 from each pair. And if you cover all other, if you hit all other sets, then this means that this assignment actually satisfies all the clauses. Otherwise, there are no such assignments. So this is equivalent to the original SAT problem, right? But the bad thing about this reduction is that you create an instance of the heating set problem of size 2n. Your universe here is of size 2n. You have 2n different elements, and this means that you cannot solve Heating set only in time 2 to the n over 2. Like you cannot improve on 2 to the n over 2. Yeah, this says only that under the strong ETH assumption, there are no such algorithms. But upper bound is 2 to the n, so we want to close this gap. Other questions about this simple reduction by switching to actual one? Y square root, yeah. So we start with SAT problem on n variables. We reduce it to heating set problem on 2n variables. Now assume, let me call it like n, the number of elements in the universe of heating set. I will be calling it capital N. Assume you have an algorithm for heating set which solves it in time, say 2 to the capital N, size of the universe. Then, for example, you can solve SAT in time 2 to the 2n. Is it surprising? No, it's not. But say you can solve it in time 2 to the n over 3. Then you solve SAT in time 2 to the 2n over 3. Is this surprising? Yeah, we don't know how to beat 2 to the n. That's how you get 2 to the n over 2, right? Yeah, which is square root of 2. Yeah. Good. Other questions? Okay. Recently, Tsigan et al. Said the following. Why is there a gap between this lower bound and the trivial upper bound? Because this reduction is kind of redundant, right? We reduce it to subsets of universe of size 2n. How many subsets does such a universe have? 2 to the 2n. How many subsets do we actually use? For each pair, Tx, Fx, we never have a set which contains both of them or like none of them or something. We only use one of each. We only use, in this search space of size 2 to the 2n, we only use a subset of size 2 to the n. That's why the previous reduction is redundant. And now we will try to fix this. For this, we'll say the following. We'll show that we'll start from ksat, and we'll show that for any alpha, we can reduce ksat to heating set on a universe of size slightly larger than n. Because when my universe is of size 1 plus alpha times n, then I have 2 to the n 1 plus alpha different subsets and only 2 to the n Boolean assignments in the SAT problem. So it must be easier for me. First of all, it is possible for me to map each Boolean assignment to a subset here. And second, I don't want to blow up this set to the 2 to the 2n again because it doesn't give me a tight bound. So I'll just slightly increase the universe size. I'll say that for any alpha, I can reduce ksat to a set of size 1 plus alpha times epsilon, times n. Why does this suffice? Assume you can beat 2 to the n lower bound for the heating set. Assume you can solve heating set in time 2 to the delta n for some constant delta less than 1. Then, since there is a gap between delta and 1, I can fit 1 plus alpha in between there. I can find such an alpha that delta times 1 plus alpha is still less than 1. And then, by this reduction, I would solve ksat in time exponentially better than 2 to the n. In particular, I will solve like every ksat in time less than 2 to the n, and this contradicts SETH. Okay, so the only thing left is to show such a reduction. I want to say that for any alpha, I can reduce ksat to heating set on the universe of this size. Is this clear? Once I show it, we have a tight lower bound. Sorry? Right, yeah. Question was whether k and alpha are independent. They are. Just for every alpha, my reduction will work for sufficiently large n, but that's fine. Okay. We'll start with the following. We fix some constant p. It actually depends on alpha, but I skip some technical details here. So we fix some constant. It might be sometimes large, but it is a constant though. Just a function of that alpha, which is constant. And we define p prime to be p plus 2 log p. And we also round it so that it's odd. The idea will be the following. I will partition my input variable, my sat variables into n over p groups, each of constant size. And once I'm looking at the group x1, xp, there are 2 to the p Boolean assignments to them. And I'll actually be mapping them to subsets in my Hissing set problem of a set of size p prime. P prime is slightly larger, so I have some freedom in choosing how exactly I'll be mapping them. And that's why I'm choosing p prime slightly larger than p. So again, I split my variables into n over p groups of size p is constant. And for each such a group, I introduce a new part of the universe in the Hissing set problem of size p prime. For example, this will be u1 elements which correspond to the first group of variables. Size of u1 is p prime, slightly larger than p, and size of the first group of variables is just p. Good? Okay, now let me define for each group A sub I will be the set of, recall that p prime is odd, so I can be talking about subsets of size p, p prime minus 1 over 2, and p prime plus 1 over 2. So AI will be the set of all subsets of size slightly less than a half. And A sub I prime will be the set of all subsets of size slightly greater than a half. And note that the size of these two sets is, like by some known formula, is at least 2 to the p prime over p prime. And since p prime is greater than p by a couple of logs, this gives us more than 2 to the p. In particular, I can map all the Boolean assignments to this group into just, say, elements of this form, into subsets of size slightly less than a half. That's exactly what I'm going to be doing right now. For each group of variables, I fix like arbitrary injective mapping from all the assignments to p variables into subsets of size slightly less than a half. Now, for each clause, recall that we're talking about k-sat, constant k. I take all the groups of variables which intersect with this clause. If some group contains a variable from the clause, I take it. But together, these groups, since I have at most k groups, I'm working with k-sat, and each group is of constant size p prime. Together, all these groups contain only k p prime, that is a constant number of variables. I go over all possible assignments to these variables. There is still constant number of them. It's like terribly huge. It's 2 to the k times p prime. But it is constant. And among all these assignments to these variables, I choose those which don't satisfy a fixed clause C. Yeah, so we fixed the mapping, that's clear, right? Yeah. Now, for every single clause, I'm going to be looking at, first I'm just looking at what groups of variables intersect this clause. Since this is k-sat, constant k, there is at most k such groups. Each group was of constant size p prime. Now I'm looking, so I have the set of size p. So, yeah, right, it must be p. So I'm looking at this kp, at most kp variables. This is constant. Now looking at all of Boolean assignments to them, 2 to the kp, and among them, I choose those that don't satisfy my chosen clause C. Okay, and I take union. Each of these groups is mapped to a subset in the corresponding part of the universe. These k groups together are mapped to their union. And I'm taking all the assignments which do not satisfy my clause C, take all the sets, and add to my instance of the hissing set problem. And I'm almost done. Also, except for these sets which don't satisfy the clause C, for every clause C, of course. Here, I'm also adding AI prime. Just to recall, those are subsets of every group of size slightly larger than a half. That's it, that's the whole reduction. I'm just taking, in my family of sets, 2 kinds of sets. One which I get from non-satisfying assignments, and the other group are those subsets of size slightly larger than a half. Okay, now I want to prove that if there exists a hissing set of the size, I will explain what the size means, then formula is satisfiable, otherwise it's not. So I have n over p groups here. For each group, I want to have a subset of exactly this size. P prime plus 1 over 2, slightly larger than a half. This is why I want to find the hissing set of this size. Now I just need to show satisfiable. I can hit all the sets, and if I hit all the sets, formula is satisfiable. Let me start with the first one. Oh yeah, I forgot to say, here the size of the hissing set instance is very good. It's just, I have n over p groups, and each group in the hissing set setting is of size p prime. So my size is n over p times p prime. And p prime is just tiny bit larger than p, so this gives me less than 1 plus alpha for any alpha. Right? Okay, let me show you the first direction. If formula is satisfiable, then I can't hit every set. Here's how I do it. I'm going to be hissing with the set H, which I construct as follows.
So by saying for any alpha, you mean that for any alpha you can find the p?
For any alpha, yeah, I find a p such that this is less than 1 plus alpha. From this p I construct p prime. I still have like everything constant, k, p prime, all the assignments which is 2 to the kp. This is still constant, just constant will be huge, but that's still a constant. Okay, now again I want to show that if x is an assignment which satisfies phi, then if I construct my set in this way, it hits all the sets I need to hit. What does this way mean? For each group, what do? I first map the corresponding variables of x into a set of size slightly less than a half. And then I take its complement. I take a set of size slightly greater than a half. That's all what I do.
What is UI?
UI is this group. You remember we have n over p groups of elements in the hissing set universe. I call them UIs. I also, for each group, had a mapping of all Boolean partial assignments into sets of size slightly less than a half. You give me an assignment, I map it to a set of size slightly less than a half, and then take its complement, which is a set of size slightly larger than a half. This way, first of all, I have the correct size of my hissing set. For each group, I have exactly that many elements. And second, I need to show that I hit every set that I need to hit. There are sets of 2 kinds. One of them is those AI primes. It's easy to see why I hit each of them, because in every UI, AI prime is of size larger than a half, and my set is of size larger than a half. So they must intersect. They cannot be disjoint because they, just by cardinality reasons. So I definitely intersect each of them. There is other kind of the sets I have in my heating set instance. For each unsatisfying assignment, I had that mapping in my family of sets. So let me prove that I intersect every non-satisfying assignment here. So H is constructed from a SAT assignment. This is a non-satisfying assignment, so they must differ. How did we define our set? It's the complement of actual mapping of the assignment. So it means that this non-satisfying assignment, when it's restricted to a specific group of variables, it must differ from the complement of what I've taken here. Now I just want to say that my set H does intersect this non-satisfying assignment. How do I say it? I want to say they intersect even in the group U sub I. Because U sub I has size P prime, I intersect each of them just by definition on a set of size greater than a half, slightly greater than a half. The mapping of non-satisfying assignment intersects just by definition, how I took it, on a set of size slightly less than a half. And the only way for two of them to be disjoint is to be complement of each other. But I know they're not complements of each other, just because here I've taken the complement of a SAT assignment and you have a non-SAT assignment. So I know these two sets are not complements of each other, and on the other hand I know that sums of their cardinalities is exactly the universe size, UI size. So they must intersect. This way I actually prove one direction. I say that if formula is satisfiable, then there is a heating set and it's easy to construct it. The other direction is also simple. You say that assume you have a heating set of the correct size. First we'll say that in each group it must contain exactly slightly less than half elements. Because we know its total size is at most slightly less than a half times the number of groups. Plus, we also know that it does intersect every set of size slightly greater than a half. That is, assume that your H contains only P prime minus 1 over 2 elements in some group. I've taken all these sets into the family of sets which must be hit. In particular, I've taken the complement of your set. You don't hit it then. So in each group, you must be of this size at least. But your total budget is this times this. So this means from every group, you take exactly that many elements. Okay, and again, once I know that you have exactly that many variables, I can map this back to a satisfying assignment. Now, because all of these elements are images of Boolean assignments. So I can map it back to a Boolean assignment, and again, like basically following the same kind of reasoning, I can say that this assignment must be a satisfying one. That is, we just reduce for every fixed k, we reduce k sat to a heating set of almost same size, which means that any improvement on the heating set problem would lead to an improvement in the satisfiability problem as well. And that's it. Yeah. Sorry, say it again?
In the slides, how we decode is that?
Oh yeah, that's very good. Look, when I was proving the first direction, I said I'll take for every group, I have this mapping. Mapping gives me a subset of size less than a half. And I take its complement, this is greater than a half. Now I know that in every group you have exactly slightly greater than a half. Which means if I take its complement, I can map it back to a Boolean assignment for this group of variables. And I do it for every single group of variables, and I have a good Boolean assignment to all variables. Any other questions?
Could you possibly repeat the last 20 minutes?
Yeah, easily. Personally after the class, yeah. That's it. Thank you for your attention.